We'll move on to average value of a function. So this I do want to specify as we work through this, and I guess as you start to see more questions put together, this isn't finding the average rate of change of a function. The average value of a function is something different. So as it says on top, the first part I'm just explaining or kind of showing you what the formula is and then why it is what it is versus me just giving it to you. If we had a finite set of data, we would know how to calculate the average, or hopefully would know how to calculate the average. You would add all of your data together, divide by the number that you have. So if we had 5 numbers, add all 5, divide by 5, that's your average. The issue here, or I shouldn't even say issue, but what we run into when you have a function, even if it's on a closed interval, you still have infinitely many values of your function in that interval. So how do you find the average value of a function if you have infinitely many values in your list? So this is where we are going to be using an integral, but I'm trying to set it up to show you why you use an integral. So it says let's try to compute the average value of a function, just a general function y equals f of x on a closed interval from a to b. So we start out like we've started out areas, like we've started out volumes. We first divide a to b into n equal subintervals, so each with length delta x, so b minus a divided by n. And then we'll choose, this again is the notation for a sample point, so x sub 1 star would be any x value in the first interval. So you choose sample points from successive subintervals, and you calculate the average of the function values you get using those sample points. So I'm going to try to write this out to help it make more sense. So first of all, if we divide a to b into n equal subintervals, I'll just list a few. So we would start out with the interval, I'll say x sub 0 to x sub 1, where x sub 0 would be your a value. And then your second interval would be x sub 1 to x sub 2. And then you would have x sub 2 to x sub 3, all the way up to your very last interval. You're ending with x sub n, so you'd have x sub n minus 1, and then x sub n as your last interval. So whatever your interval a to b is, whatever your n value is, take b minus a, divide it by n, you'd get your intervals. And then here, they're choosing sample points from successive subintervals. So x sub 1 star would be some value from that first interval. And then x sub 2 star would be some value from the second interval. X sub 3 star would be a value from the third, and so on. So x sub n star would be the last sample point. And that could be a right endpoint, it could be a left endpoint, it could be the midpoint of the interval, just any value within each interval. So then what this is saying is then we can take the function value at each of those sample points and find the average of those function values to get an approximation. So we'll say, I'm just going to abbreviate average here, AVG. So the average value of the function would be, again, the function values of these sample points added together. So I would have f of x sub 1 star plus f of x sub 2 star plus f of x sub 3 star plus all the way up to f of x sub n star. And I would add all of those together. I have n function values, so then I would divide that sum by the number of values I have, so divide it by n. So that would be an approximate function value. But again, where we kind of grew with integrals, especially with areas, is we said, okay, here's an approximation. How do we make it exact to get to the integral? So this is going to take some rewriting. So from here, what's going to happen is I'm going to rewrite this denominator n, knowing that I have an expression delta x, which is b minus a divided by n. I can rearrange this to have n equals something. So if you think proportion-wise, I can think of the delta x as being over 1. With a proportion, you are allowed to switch the diagonals. So I can say here, n, therefore, would be equal to b minus a divided by delta x. So I'm getting that from here if I solved that for n. And then I'm going to replace the n in this denominator with b minus a over delta x. So I'm substituting that expression in here. So my expression becomes, still have all of my function values added on the top. And then that would be over b minus a divided by delta x, so I get this complex fraction. And rather than leave it as a complex fraction, I know I can then cancel out this denominator, or rather, dividing by a fraction means I'm multiplying by the reciprocal. So if I wanted to cancel out this denominator, I can really multiply both the top and the bottom of this overall fraction by the reciprocal of b minus a over delta x. So I can multiply by delta x over b minus a. And that would cancel out the denominator, but then I would also have to multiply the top by that reciprocal. So I get my sum of function values along the top multiplied by delta x over b minus a. And I'm going to rewrite this. This is what I have. I'm just going to rewrite it in a different form. So I'm going to kind of break this apart. So I'm going to break this delta x over b minus a as having a 1 over b minus a in the very front. The delta x is going to stay multiplied at the end. So I have 1 over b minus a times the quantity of these function values added together. And then that quantity at the end, I'm multiplying by delta x. So I just kind of split that. Part of it's at the beginning. And the reason why I'm doing that is now, aside from the 1 over b minus a, the sum of those function values added together times delta x, I could write that as a Riemann sum. So I can write this as 1 over b minus a times the sum from when I is 1 to n of f of x sub I star times delta x. Okay, this is kind of like a proof, but you're not going to have to mimic this. Okay, so that's kind of replacing, again, all of those function values added together times delta x. The reason why I'm writing it in this form is, again, this is an approximation for the average value of the function. This is only an approximation. So if you wanted the exact value, yes. So then you would say from here, if n were to approach infinity, you would have the, let's see how I want to write this. I'm going to write the 1 over b minus a, since that would be a constant or a coefficient. I could write that in front. So I would have 1 over b minus a times the limit of this Riemann sum, the limit as n approaches infinity, yes, which will give you the integral. But then you see why you're using an integral to even find this. So this then, limit of a Riemann sum is an integral, so you really have 1 over b minus a times the integral from a to b of your function f of x dx. Yes. And that is then the formula you use. Anytime you're asked to find the average value of a function on a closed interval from a to b, this is what you find. You take 1 over b minus a and multiply it by the integral from a to b of your function. Okay, so you can fill that in here as well. So you actually have the definition kind of written away from all of this proof. So average value of f on closed interval a to b. Sometimes they write it like this as f sub, and then as a subscript AVE, so the average value of f is 1 over b minus a times the integral from a to b of f of x dx. So that's a formula that you need to know, and then as we work through problems, know when to use it. Some formulas will be explicit, just find the average value. Other times your function might represent a specific quantity, like your function might represent velocity and they want you to find the average velocity on an interval, then that would be using this. Okay, so that is why we use an integral to find the average value. Now to actually use it, so we have find the average value of f of x equals x times sine of x squared on the closed interval from 0 to the square root of pi. This is just reviewing some integrals as well. So the average value of f, I'll say f sub AVE. Using this formula, a value is 0, b value is the square root of pi. So I would have 1 over b minus a is the square root of pi minus 0, or if you just wrote square root of pi, times the integral from 0 to the square root of pi of my function f of x, so of x times sine of x squared dx. Now I included this function specifically to review how to find this integral without using a calculator. So the setup is using the formula. Now actually finding the integral is just reviewing how to do that. So again, when you find an integral, what do you have to find? Antiderivative. Do we have an antiderivative for the product x times sine of x squared? We have to use what? We have to use substitution. You have to use u for this one. So what would you choose? This is reviewing substitution, Dylan. X squared. And again, if you choose a u and it doesn't work out, try something different. So u is x squared, so this becomes sine of u. I then still have an x and a dx to get rid of, so I have to be able to get rid of that with the du. So what is du equal to? 2x dx, derivative of x squared, is 2x. I don't have the 2, so you divide both sides by the 2, so 1/2 du equals x dx. And now the x dx matches what I do have left over in my integral. And the 1/2 can be written in front of the integral right away. So I also have a 1 over the square root of pi in front of the integral. So I'm going to write the 1/2 in front. So I have 1/2 times the 1 over square root of pi that was already there, times the integral from. Now, this is where I would recommend when I'm writing everything in terms of u, I should also be writing the limits in terms of u, unless you rewrite the integral in terms of u, change it back to x, and then put these values in. But some AP questions require, just with multiple choice and how they write the answer options, they require you to change these values. So don't rewrite 0 to square root of pi, because those are x values, they're not u values. So if x is 0, you just substitute it into your u here, then u would be 0 squared, so u is also 0. And then if x is the square root of pi, u is the square root of pi squared, so u is just pi. But now I can leave everything in terms of u. I never have to change it back to x. So then I have 0 to pi. My integral just becomes sine of u, and then du. But I do have an antiderivative for sine of u, so now I am able to take the integral. I'm going to write this in front as just 1 over 2 square root pi times, what is the antiderivative of sine of u? Negative cosine of u, and that's evaluated from 0 to pi. So notice I don't have to change back to x. I'm not putting x squared back in. I'm not changing these values. Everything is u right now. So I have 1 over 2 root pi times, substitute in pi, so cosine of pi is, negative 1, so the opposite of negative 1 would be 1, minus cosine of 0 is 1, but the negative makes it negative 1, so I have 1 minus negative 1. So I really have 1 over 2 square root pi times 2, so it's 1 over the square root of pi would be the average value of that function from 0 to the square root of pi. Okay, so realize the new part of that problem was using this formula. The setting up, as long as you remember the formula isn't challenging, but then actually remembering how to find the integrals, it may involve substitution, it may not. But if you have to work it out by hand, make sure you understand how to get the antiderivative or how to use substitution. The second part, there's another part to example 1. It says, is there a number c, where c would be an x value, is there a number c at which the value of the function f of x is exactly equal to the average value of the function? So that is where f of c is equal to the average value. There is a theorem called the mean value theorem for integrals that guarantees a number of the, or a value of the function equal to the average value. So as long as your function f is continuous on the closed interval from a to b, then there does exist a number c in that interval such that the function value is equal to the average value. And it does give a graphical description. So this is just written, function value is equal to the average value, but you can also see this here. So how they're getting from here to here is they're multiplying both sides by the quantity b minus a. So you just get this integral is equal to f of c times b minus a. So really the geometric representation of this, which I've included here, what it's showing is that by that mean value theorem for integrals, there exists a value c in the interval from a to b such that the area of this rectangle is equal to the area under the curve. Because if you look at this rectangle, this piece that's under the curve is really here as well. So that's the geographic or geometric representation of what that states. So overall, what we're going to practice with the second part is just finding that value. So if you needed to find the value, that's guaranteed by the mean value theorem for integrals. So find the value, find the function value f of c, or find the value of c, I should say, such that f of c equals the average value. And this is from example 1, so we already know the average value is 1 over the square root of pi. Same function, same interval. So we are trying to solve, or we know rather, f of c is equal to 1 over the square root of pi. We're trying to solve this equation. So what this looks like, and if you kept it in terms of x, that's fine. What this looks like, though, is you would replace in your function f of x, you would replace the x's with c's. So you're solving c times sine of c squared equals 1 over the square root of pi. You're solving that for c. You're trying to find the value of c, or if there's multiple, the values of c that satisfy that equation. And again, I included this function on purpose. 1, the integral requires substitution. 2, how do you solve this equation? Graph it, yeah. So don't forget, if you are allowed a calculator, that to solve an equation, you can graph both of these and find where they intersect to solve that equation. If it's not something that seems easy to solve by hand, use your calculator. So I would want to graph, I'll put for y sub 1, x sine of x squared, so the actual function, and then for y sub 2, put the average value so I can find where they intersect. So 1 divided by the square root of pi. And I'll graph this just starting out. Oh, yeah, I should have actually done. I'm going to stop this. I'm going to go to the window and limit the x min and max to be the actual interval. So limit the x min should be 0, x max should be the square root of pi. And then I may need to change things here. There may be 2 points. You'd have to find both then. Yeah, so the mean value theorem for integrals just guarantees at least one value exists. There might be multiple. I'm going to, not that I would have to do this, because the intersect feature would still work. I'm just going to change my window again. I'm going to change my y and min and max to not be as great of an interval. So I'll do maybe negative 4 to 4. It's zoomed in a little bit. Probably could have zoomed in more, but you should see for this there are 2 intersections. So that means 2 values of C satisfy that mean value theorem, and you'd have to find both. So you'd have to, just as a review, go to second trace for the calc menu. Option 5 is intersect. It'll ask first curve and second curve. Just make sure your cursor is closer to the intersection you're trying to find. And round to 3 decimal places. So 1 occurs when C is approximately 0.851. They will not. And then the other one is approximately 1.673. Like twice this. Almost. Yeah. Okay, and if there's a problem, from the assignment, if it asks you find the values of C that satisfy the mean value theorem for integrals, this is what it's asking you to do. Set your function equal to the average value and find those values of x where your function would equal that. So I just have, for example, 2, this is just for you to do on your own. Just a practice problem. Find the average value of that function on the given interval, and then find the values of C that satisfy that mean value theorem. So do example 2 without me. And then there's some practice there for you, but like I said, if you have questions from last week or from Friday, we have time to go over questions, or I can walk around and answer individual questions too.